Hello and welcome everyone to our today's presentation about memory utilization. In today's presentation, we will go and have an overview of the Big IP memory, understanding the Big IP memory statistics, go over examples of memory leaks in TMM and host processes, and troubleshooting and diagnostics tools with examples as well. And we will finish with a quick summary. When administering a Big IP system, it is important to understand how the system allocates memory. In general, the Big IP memory usage falls into the following categories: the traffic management microkernel, the TMM memory usage, the Linux host memory usage, and swap usage. TMM runs as a real-time user process within the Linux host operating system. The Big IP system statically assigns memory resources to TMM and potentially to other model-related processes, depending on the model provisioning. The remaining memory is available for all other Linux host processes. And the Big IP system creates swap usage space during software installation on disk. And this is swap space is available to the Linux kernel. The following information summarizes TMM memory. So the Big IP system assigns a dedicated pool of memory to each TMM process. TMM memory is not available for the Linux kernel to reassign to other host processes. The system never considers TMM memory as available. This is important to note. The TMM memory cannot be swapped to disk. The TMM memory management subsystem allocates and clears memory pages in the following manner. TMM allocates static memory to hash tables, for example, the connection flow table. TMM also dynamically allocates memory pages for temporary objects, for example, persistent records and buffer connections data. Memory sweepers periodically read unused memory as needed from TMM objects. And when possible, TMM caches dynamic allocations to improve performance when new objects require the same allocation. The following information summarizes what the Linux host memory usage is. The Linux allocates most available memory to buffers and disk caching, which gives the appearance of high memory usage, but allows the system to run more efficiently. Linux utilities such as top and free may report that only a small amount of memory is free. And there is nothing to worry about. This is a normal behavior. Cache memory can be reclaimed quickly if a program needs memory. To see memory used by buffers and disk caching, view the -+ buffers cache row when the top and free report these memory structures. Add these values to the reported amount of free memory to estimate the total amount of physical memory the processes are not currently using. The Linux kernel sometimes copies memory pages to swap. This is known as swapping memory. The following information here in this slide summarizes the swap memory usage. It is normal for Linux system, including the Big IP system, to use all small amounts of swap. The Linux kernel sometimes prefers to swap idle processes memory to disk, so that more physical memory is available for more active processes. Buffers and cache. Physical memory is much faster than swap. Prioritizing buffers and cache allows the kernel to optimize performance of disk-heavy processes such as databases. A higher percentage of swap use is normal when provision models make heavy use of the disk. These models, for example, could be ADR or ASM that they handle and write to disk with the database. The excessive swap usage may be sign that the system is experiencing memory pressure. So you should investigate in the following cases. If the system uses a very high percentage of swap memory, the rule of thumb will be 300 megabytes swap. Above that, they should be investigated. And the percentage of swap memory usage increases over time. So you can view big IP memory statistics using big IP utilities or Linux command line utilities. It is normal for Linux utilities, as we mentioned previously, such as stop and free, to report small amounts of free memory. And this is expected, and there is nothing to worry about. F5 recommends that you use the configuration utility or the TMOS shell, the TMSH, to view memory statistics on the big IP system. Using the TMSH show sys memory, or via configuration utility, go to statistics, module statistics memory. Here we have an example, and typical case when we got my system has a little free memory, therefore I have a problem or a memory leak. So here you can see on the memory free is 87. So unused core memory is conserved in this cache. The first line of the output from the free command that shows a little free memory may be misleading. If you pay closer attention to the second line of the output, which shows the actual amount of RAM available for applications, the reason the OS operating system allocates a significant amount of memory for this cache is because the RAM is wasted if it is not used. If it is wasted, it's not used. Memory cache ensures that if the process requires to access the same data again, there is a good chance the footprint will still be in memory. Fetching information from there is around 1,000 times quicker than getting it from the hard disk. If it is not found in the cache, the hard disk needs to be read anyway. But in that case, nothing has been lost in time. In BigIP version 11.6.0 and later, the configuration utility and TMSH report memory allocated to buffers and cache as free memory. This indicates that cache memory is generally available for use by other processes. The memory statistics are reported as follows. So we have the system memory, the TMM memory use, the amount of memory in use by the TMM processes for traffic management. The other memory used is the amount of memory in use by Linux or non-TMM processes. The total memory use is the sum of the TMM and other memory. And to finish, the swap use, the amount of swap space used by all systems processes. In previous versions, for example, from 10.x to 11.5.4, the configuration utility TMSH report memory allocated to buffers and cache as used memory. As a result, it may appear that the host system is using all available memory. The system memory statistics in the following ways, as you can see in the screenshots. The host total is the amount of the memory available to the Linux or non-TMM processes. The host use is the amount of memory in use by the Linux or non-TMM processes. The TMM allocation memory is the amount of memory available to TMM processes. And TMM use is the amount of memory induced by the TMM processes for traffic management. So we enter into troubleshooting and diagnostics tools. So the jump-off point of troubleshooting suspected host memory leak, when we're talking about a leak in the host memory, is to look, the first thing is to look the top output taken in the QK view, or you can do this on the live unit as well. As we can see here is around 382 megabytes. So as we discussed earlier, our rule of thumb, it will be 300 megabytes. So this needs to be investigated. In iHealth, you can search for the top command and sort by resident memory, or swap, which may provide clues on host processes taking memory. So then a QK view taken later on, that we will see on the following slide, it shows a swap almost maxing out. At this point, we can see the memory is nearly maxed out. You can see that the swap here is around 1 gigabyte. So which is enough evidence that there is a leak on the host, on memory host. So what could happen if the swap max out? It reaches a certain point that processes needs memory. You will see the error messages on the kernel log, the killer. So these messages occurs when the following conditions are met. One or more active processes have consumed an excessive amount of memory, which may be due to the process failing to release memory properly, also refers as a memory leak, or the Linux kernel overcommitting memory and allocating more memory to process than is available. Little available memory remains for use by other system processes, also referred to as a memory pressure. So when the BKP system processes experience memory pressure, the Linux killer scores and kills or sacrifices one or more processes while attempting to free memory. So you can see, this is an example. What you can encounter, these messages are stored on varlog kern.log. And in this error message, we can note the following. The process ID, which is the numeric identifier used by the Linux operating system to uniquely identify an active process. The process name is the alphanumeric or human readable identifier for an active process. And the score value is based on the percentage of memory being used by the process. Processes are killed by higher to lower values during an out of memory condition. So for this example that we can see here is the HTTP process invoked the killer, and we can see the out of memory kill process, and basically it killed the Java process. When the killer is invoked, the impact will be that the BKP system may stop processing traffic. You can experience a failover event or become unstable due to one or more processes being killed by the killer. One command that you can use to search for if the killer was triggered is the one that you can see here is the grep invoke killer on the kernel log. So there are two ways that system memory will recover when we're talking about host memory leaks. The BKP was either rebooted automatically or as a result of tipping over or manually. And demons killed to freeing that memory. That would be the killer, as seen in the previous example. When we are looking to troubleshoot TMM memory leaks, now we're talking about TMM and not host. The starting point for troubleshooting suspected TMM memory leak is either the graph in the QK view or reviewing the command sections in the QK view for the following command. DMSA shows its memory. In the QKV memory graph on the next slide, a leak in TMM can be observed, but to determine the memory object that is leaking the memory, we require looking at outputs. So this is an example of memory leak on TMM. We can see that the TMM use memory line on the graph is constantly going up. So now that we suspect that there is a leak on TMM, an inspection of the output shows its memory will give us more information and probably the culprit of the issue. The command from the same, you can run the command on the QKView or the live unit. And for that particular example, we can see that the source address translation process is consuming all the allocated and resident memory, 3.6 gigabytes of memory. And this is caused by a known issue. If you want to check in detail, you can review that solution article. And when the unit experience TMM memory leaks or TMM memory pressure, the impact of this leak can be seen in the following slide. The system will enter in aggressive ripping mode to try to free up the memory when memory leaks persist. A simple calculation to determine the percentage used by each TMM is by running the command TMCTL -d blade TMM /pagem. The output will be similar to this, but we can see the pagem and the use and the available. So the calculation is the use divided by the available times 100, and that will give us the percentage of used TMM memory. Using the previous example, you can see here that we're talking about 84, 85% of memory used. So when the BKP reaches that point that it needs to start ripping connections of the sweeper, the aggressive sweeper is triggered, you can find on the LTM logs this particular message that it will be an indicator that the aggressive sweeper is being triggered. You can see that the aggressive mode sweeper and it killed 13 connections. So the sweeper is the component is the component within the traffic management microkernel, the TMM core that both watches for expired connections flows and responds to resource exhaustion by adaptively ripping connections flows. This in order to help prevent resource exhaustion. Connection flows are removed once they have been idle for longer than the configured idle timeout value. To help mitigate possible attacks or overflows and system flows, the adaptive connection ripping feature monitors connection flows and system resources to dynamically adjust how aggressively and what connections flow to remove or rip or prevent. The aggression level is determined by the distance traveled between high and low watermarks. At or above the high watermark, the aggression level reaches 100%. Below the lower watermark, the aggression level is 0%. And halfway between the high and low watermarks, the aggression level is 50%. So these are the DV variables that you can see on the top of the slide that controls the level of the watermark, the high and low levels watermark. As soon as the BKP, the low watermark is reached, the TMOS will begin killing connections to try to free up some memory. And once the memory usage reaches the higher watermark, the sweeper is set it to the most aggressive and rapidly will kill all the connections to prevent system failure. To expand on this information, you can review these solution articles. Okay, and before going to resources and known issues, we will now do a hands-on example. Okay, checking. Please bear with me. So to locate the device is this one. Okay, so we have here one big IP unit. Let's check on. Let's do all type of checks via GUI, via CLI, and also via iHealth. So we have this unit, and we will check here the performance to check what is the memory usage on this one. And we can see that the memory use, the swap used, is very high. It's almost maxed out. So let's go now to check via CLI. Okay, we start obviously with subcommand. And what we would like to focus here, because we already saw on the graph, is that the swap memory is almost 900 megs, which is above of our expected or rule of thumb 300 megs. Now we will run a TMSH shows this memory. So we can see here how is the memory distributes. On the TMM, we can see that the TMM process has allocated 3 gigabytes. From those, it is using around 300 megs. And we have almost 2 gigas 900, yeah, almost 3 gigas available on the TMM. This is that will be the host memory usage, and the swap that we can see that is really high. And here we can check per process. Now let's review using the TMCTL command. So we will need to go to cd share TM stats snapshot. Where is the TM stats snapshots are stored. And as you can see here, this is all the snapshots per day from the 21st of November to the 27th. So what we can do is to start reviewing each of those snapshots. So the first one is 21st. Let's filter just to see the top 10. So what we like to see, because we are just troubleshooting memory, we're going to filter for the process name, the allocated virtual size, and the resident size of that process, and to get a top 10. And we can have here an idea. This is the V size and the resident. Basically, here, one thing that you can do is review if the processes are reaching on the resident memory is reaching what is the V size, the allocated size. That will be a good indication of which process could be leaking memory. And the other, if we can see here, that is all of them are quite low in comparison of what they are expected. You can still reviewing by date to see if you can spot a leak. So for TMM, you can see that it went down here. It went down here also. ASM config server, it seems that it went up. In Java and AVR, AVRD went down. So so far we didn't have a particular process to point out as the culprit for this issue. Let's continue reviewing per date. Everything is mostly the same. So it doesn't look like a leak. There is no a drastic change or even a little one that you can notice that is increasing over time. So at this point, let's say that you don't know, you're not working on the live units, you're working with a QK view. You can run exactly the same commands on these commands on a QK view if you extract the QK view into a Linux box. Just like extracts the file and you can run exactly the same commands. Let's confirm what models are provisioned. As we mentioned at the beginning of the presentation, the memory allocation and memory utilization will vary depending of what models are provisioned. We go back to TMSH and list sys provision. And we can see that this unit is provision 3 models. We have AFM as nominal. We have ASM as nominal and LTM as nominal. So 3 models are provisioned. And let's confirm what this is VE. So let's confirm what is the total available memory assigned to this virtual machine. Okay, so it's roughly 8 gigas. So we have to consider and know that we are talking about a three-model provisioning. ASM, one of those that it is tends to be resourcing intensive, and this virtual machine particularly has only 8 gigabytes to allocate all that. Okay, so let's assume now that we are working with a QKView instead. The first thing is to review what version are we running. This is 13.1.7. Again, from here we can see, yes, we have 3 models provision: LTM, ASM in, and AFM. First thing that I would recommend, because it could save you time, in some cases you can spot here fairly quickly if it is a known issue, particularly if we're talking about the killer that it was triggered and killed some processes, you will see it here. So it will give you an idea that what process is being killed, and from there start building up and investigate it if it could be a leak with that particular process. In this example, we don't have anything valuable from the diagnostics page. So the second will be check the graphs. Now that we have our results, we go and check the memory utilization. We can see that at least for this unit, it's been a long time that is experiences this memory pressure and high swap usage. In all other scenarios, when the memory leak just started, you can see the sawtooth behavior of the blue line going up and immediately down when the system performs something, or killer, or it failover, or a reboot. So from the QKView tools, we can go to commands and check exactly the same that we did on the live unit. We can search first and top. We can see here that the swap is high, as well as in the graphs. And important to know what is the total amount of memory that virtual machine has available. And here you can order the outputs based on resident memory. Here we can see, because if you order by size, is based on allocated, and it will not give you an idea what is what actually the process is consuming. So that's why we recommend to order by residence. We can see the top processes here. TMM, which is normal, is under normal levels. ICRD child, and ASM config server. We can see that is almost or reaching the residence. And once you order by resident, you can also order by swap utilization. This doesn't mean if you have a particular process that is consuming swap that the the process is causing the leak, probably because there is memory pressure as well. Unit decided to send that process to swap just to be available to other important processes. So we have Java and scripty. So from our review, you could check once on a resident. This one, ASM config server, that it looks close to the size. If that could be a possible leak with that one, then just to go to Ask F5 and review if there is something for that particular process. We can do an example right now. Let's go to Ask F5. If something pops up, this is for a high CPU. Let's just check for ASM config server. Just add the word leak. This is one. The ASM device group members may experience memory leak in the ASM config process. So we will just review that this is an old bug and doesn't apply to our example that we are running 13.1.0.7. From here, as the same as we did on the live units, we can keep running commands. Show sys. I'll just go with memory. Yeah. The host available in TMM. And here you can order by max allocation, allocated bytes for a particular process. And limited version of what we did with the TMCTL commands on the live units, you can do it here. This is a TMCTL memory. But it should be this one, TMCTL-A. And from here, the proc process ID stat. It is simpler on the live unit because you can just filter for what you're looking for. Here we can see the V size and resident memory. Now we order by resident memory. And we have our top consumers. So in this particular scenario, it is important to note what I tried to show you at the beginning. When you just run the top command, and we know that this unit has only 8 gigabytes of RAM available, and there are, let's go to the back, 3 models provision, which ASM, we know that that is resource intensive model. So with a little bit of researching, we get this one. The big IP ASM system may experience memory capacity issues when more than one model is provisioned. So basically, we have, this is the important part here. The system permits provisioning by both big IP ASM and big IP LTM as nominal in an 8 gigabytes VCMP guest or VE. So although it allowed you to provision, however, you should provision the big IP ASM system as dedicated to allow the maximum available memory for the big IP system ASM. If not, you will see this increase in swap usage because the host needs more memory to handle all the ASM features with the traffic. So let's say if you are, this is a VE, or if you're working on a VCMP guest, that's if you are facing this issue, since it is a virtual machine, you can add more resources, add more memory to the virtual machine, or a VCMP guest as well. You can add more vCPUs to expand, so you can expand the memory. Let's say if you are on a platform, on a box that you can expand the memory, you will need, and this time you have a few options. One is when we review here the TMM, let's check again the memory. So one option here, we can see that TMM, since is provisioned as nominal and is allocated, it allocated 3.2 gigabytes to the TMM process. But actually, this unit is using almost 300. And on the graphs, we can see that that is consistent. So allocating that amount of memory to TMM and it is not being used, you can say that there is a waste. And when ASM needs more memory, that is why the swap is increasing. So one option is to set the LTM to none. By setting LTM to none, you will not lose any LTM functionality. The functionality is per license, not by if it is the provision is set to none. And this will, let's say when you provision to none, it will give something around 1 gigabyte to TMM, and the rest will be to the host for the ASM to use. If you are, this is a caveat with this option. If you, if in the configuration there is IAPS, some IAPS relies on this amount of memory that the TMM has allocated. So you cannot deprovision or set the LTM to none. At that moment, the only way is to escalate the case so we can provide to you a custom provisioning table. So we will review the resources on the unit, basically what is the TMM usage for a period of time, and from there create a custom table so we can accommodate what TMM uses and give a little bit more memory to the host. And well, also if you have a model provision that you are not using, of course, consider to deprovision the model if you are experiencing this kind of memory pressure. So let's go back to our presentation. Well, and here you will find some of the resources and known issues that we cover on this presentation. Basically, the overview of the PKP memory, how to understand the statistics, and where to look at. And the last one is the one that you just pointed out. That is really important to have that in mind when there are limited resources and there is more than one model provision. Even and more important if ASM is also provision along with LTM. And our quick summary from this presentation, the TMM and host memory, what we learned is that they are separate. Even though TMM is also a user space daemon, its memory footprint is fixed. The TMM does not contribute to host memory leaks. And the troubleshooting, as we saw, is handled separately. One from if it is TMM, you can see on the graph that is TMM is going up, and then you can review and try to locate which TMM process is generating the leak. If it is host, most likely you will see the swap increasing. And how to troubleshoot? As we saw, a combination of QK view analysis, graph, logs, TMSH commands, and is useful in both the live and the offline troubleshooting. As you saw, we can mostly do exactly what we did on the live on the QK view, except the TMCTL, but basically you will need just to extract the QK view and run the commands. And this is just a summary of the commands used to troubleshoot. The top, the TMCTL memory usage. You will need to go to CD share TM stats, snapshots, plates. You can also, this is if you want to check per day, the memory usage per day, but you can also change that per hour, changing this to 3,600. The very important one when you are troubleshooting TMM leaks, TMSH shows its memory, and the proc mem info, as well available on the QK view. And yep, that will be it for today. Thank you.